Hello, my name is Saumyabrata. I am a 700 level graduate architecture student at Miami University. Throughout my academic and professional career, I have always searched for ways to develop the architectural design process. My interest in computational design encouraged me to take a deeper look into the recent world of generative design through the minor media course. Gartner's hype cycle provides a very clear and elaborative idea about the recent hypes in technology. And as you can see in the graph, the top of the hype is led by machine learning, deep learning, and connected homes. With the help of artificial intelligence, machine learning, and digital fabrication, industry professionals have been able to develop unforeseen products that are much more efficient in terms of energy consumptions, cuts down material costs, and even works much more efficiently than traditional design. Here you see the development process of an automobile wheel. Although computational design can be traced back to 1960, the recent trend of artificial intelligence and machine learning has given birth to generative design, which is still at its infancy at 2020. Industry pioneers such as McNeil, Autodesk are leading the trend of generative design in the world of architecture, engineering, and constructions. Autodesk's recent development and integration of generative design software into Revit deserves a special credit. Autodesk is not only developing the software but also using their own design tool in practice. The video you are seeing right now is the generative design implementation of Autodesk Toronto headquarters design. The idea of this project is to develop a generative design script for Revit to optimize window placement in a certain elevation based on the geometric properties of window and wall. For this, different tutorials from lynda.com was followed and exercised to develop the program. Case studies such as three mass case studies was observed carefully to understand the different variables in generative design and how each component would work so that can be applied to the final project. At the end of the process, the script looks something like this. It can be divided into four separate sectors: the input, the generator, the evaluator, and finally the output. Let's look at each of them for easier understanding. Let's take a look at the input panel. In the input panel, there is only two elements that are measured. One of them is the wall element from the Revit, which is going to hold all the windows. That element is being converted into a data geometry, and that element also signifies the sliders, which is going to create the segments inside the wall, which is going to hold the windows. And then comes the windows. The window family is organized in such a way that it takes all the windows inside the Revit and transforms them into the geometry. And the windows are then divided into lists, which consists the list of all the windows available. Then all of these windows were evaluated into code blocks based on their width and their height. And those widths and heights were converted into parameters and turned into data sectors, so that can be used in terms of evaluating the window sizes inside the wall apertures. Now let's look at the generator sections. The generator section is the one which generates the windows inside the wall sections. It takes the wall geometry and operates the wall segments and translates the wall segments into windows. When we look at the evaluator section, the evaluation goes into two phases. One of them so the windows do not overlap with each other, and one of them is the wall length. The wall length is signified in such a way that the total number of windows do not exceed the total length of the wall, so the windows remains inside the wall. And the window evaluator sections is set in such a way that the maximum summation of the windows do not exceed and create all of them into one single big aperture. It is run through a test kit which proves the length and the width of the windows do not exceed their initial values. When the data is false, the windows shows errors and do not go through. If the data is true, it goes to the output sections. In the output section is simple. It just turns the generated dynamo model into a usable Revit model, which can be used throughout the Revit program just like any other Revit drawings. When launched from the Generative Design window, the script can be used to create different case studies. When selected, the architects can change the number of windows or the number of selections according to their wishes and what they want from the design. After the selection is done, the architects can just press the Generate button to create different studies with different results. After the generation is done, all the results are going to be shown in a display. The graph below will explain what are the different properties for each of this design. This graph can also be used to separate out each design scenario according to the choice. Here you see another scenario where different results are shown and the graph below explains each property of each design. Feel free to pause the video, scan the code, and download the script for your own design use. To summarize, it can be said that generative design saves time, makes less mistakes, produces efficient and sustainable design, which evolves over time, but it also a bit expensive and more time consuming and requires a lot of advanced knowledge about parametric design to develop scripts. Generative design is still at its infancy, but it will be amazing to see how it unfolds and pioneers the world of architectural design. Thank you.